All right. So this is going to be kind of the last video, talking kind of more generally about entropy and properties of entropy and things like that. And in next set of lectures and things like that, we're going to start talking more about specific entropy changes for specific types of processes and such. Okay, but here talk more about this Carnot cycle and how it's related to the efficiency of heat engines and the Clausius inequality. Okay, so for a heat engine, okay, a heat engine often can be approximated as this type of a Carnot cycle, right? For a heat engine, how it works is you have some hot object, right, that potentially gives energy to your system, right? And then the energy, some of that energy goes into work, and then some of the rest of the energy goes back into a cold system, okay? And so that's related with these isothermal and adiabatic changes, okay? The isothermal changes are this influx of energy, okay, and the reduction of energy, and then the adiabatic changes are going to be related within the amount of work that's being transferred, okay. So in this definition of a heat engine, okay, I have some heat that's supplied, okay, it's typically a positive value, right, because it's given to my system, right, at some high hot temperature called TH. Some work is being produced, right? That work is less than 0, so in this figure here, it should be a negative sign, not a positive, okay? Right, work is less than 0, right, because the system is doing some sort of work on the surroundings, okay? And then some heat is lost to the cold side, cold sink, if you will, right? And so I have some loss of energy through heat, okay? So, right, because energy is conserved, right, the total amount of energy input from the hot source is equal to the total amount of work done plus the total amount of energy taken in by the cold source, okay? So rearranging this, right, the work that's done is just the energy supplied by the hot source minus the energy consumed by the cold source, okay? Right, again, here I'm just focusing on the magnitude of these values, right, not their actual signs, okay? And so we're going to define the efficiency of a heat engine, right, as the amount of work that's done divided by the amount of energy that was absorbed by the engine, right, the energy that was taken in, okay? And so that's essentially, right, that's just saying what's the amount of work that I got out over the amount of energy that I put in, okay? And that's the efficiency, okay? Well, right, that work is related with the hot minus the cold heat transfer, right? And so that efficiency can be written as 1 minus the heat transferred to the cold side divided by the heat transferred to the hot side, okay? Right, this is for a heat engine, we're again thinking of this Carnot cycle, okay? The total entropy change is equal to 0, okay, for this process. And so the total entropy change, right, is related with the heat transferred at the hot side divided by the temperature of the hot side plus the heat transfer of the cold side divided by the temperature of the cold side, right? So I can rearrange this, okay, in order to get this relationship, okay, that this relationship here between the hot and cold heat transfers, right, and I can write QH over QC, right, equals TC over TH, okay, absolute value of these heats on the left, right? And so I can plug that back into my expression up above to get this final expression for a heat engine here, which is the efficiency of a heat engine is just 1 minus the temperature of the cold side divided by temperature of the hot side, okay? So the more extreme these temperatures are, right, the hotter your hot side is, the colder your cold side is, the more efficient this heat engine is going to be, okay? Which again, this is a heat engine, right? How this works is by just transferring energy via heat to then try to do some sort of work, right? And this is how a turbine works, right? So a turbine works by, let's say, I'm burning coal, right? I'm burning coal, I'm generating a bunch of heat, right? This high temperature to boil water. That water boils to create this hot steam. That steam goes through and turns a turbine, and as it's turning that turbine, right, the steam is giving up some of its energy, right? And this is done in an adiabatic type process, okay? And it's doing some amount of work. It's giving up all this energy, right? All of its kinetic energy, right, as work, right? And it's dropping its temperature until eventually drops back down and cools off, and then will eventually condense down to water, right? And that's sort of my cold sun, right? And then you can just repeat the cycle over and over and over and over again, right? And this is how a lot of energy in the world is generated. It's just through turbines, right? And steam heat engines, okay? And so we can calculate the efficiencies of these things based off of just this simple equation given here, okay? So now, talk a little bit about, kind of related with this, is this idea of the Clausius inequality, right? Which again, we're talking about efficiencies of heat engines, right? Right, and so the total amount of work that I can get out, right? Right. Let's think of, right, for this heat engine, right? The amount of work I can get out, right, is always greater for the reversible work than it is for the irreversible work, right? We've talked about this before, right? That the amount of work that one can do is always greater than that of the irreversible work, okay? Right. And so throwing in the fact that the work done in these things is negative, right, because it's done by the system, right, I have this relationship here, okay, right, I'm going to just, right, add over dW, right, so dW minus dW reversible is always greater than or equal to 0, okay, right, I'm going to use the fact that, right, this change in internal energies, right, is related with the amount of heat transfer and some amount of work done, and the fact that internal energy is a state function, right? So dq reversible plus dw reversible has to equal dq plus dw, okay? So, and then I'll rearrange that, right, to have dw minus dw reversible is equal to dq reversible minus dq. So I plug that into my inequality, okay? And I get dq reversible is greater or equal than dq, okay? So finally, if I divide both sides this by temperature, right, and use the fact that entropy is defined as this change in reversible heat divided by temperature, I get that the entropy change in your system is always greater than or equal to the heat transfer divided by the temperature. And this is what's called the Clausius inequality, okay? All right. And the only time these are equal to each other is when the process is done reversibly, okay? But otherwise, this entropy change is always greater than or equal to that of of the heat transfer divided by the temperature, okay? And this is always satisfied for a spontaneous reaction, okay? And this is, again, this inequality is always true, okay? So finally, let's just talk about, we're going to talk just about one specific type of entropy change here. That's for phase change, because we kind of introduced this idea a little bit in a previous video, talking about entropy change in the surroundings, right, being related with enthalpy change over temperature and things like that. And so for phase change, right, phase change takes place at a constant temperature, which is very nice, and it takes place, right, at constant pressure. It is an equilibrium process, right? Our phase changes, we assume, are changing at the phase change temperature. It is done at equilibrium, so it's a reversible process. So the heat transferred for that reversible process is a reversible heat. And the reversible heat transfer under constant pressure conditions is just related with the enthalpy change of that phase transition, right? So for a phase transition, delta S of the system is just equal to delta H of that transition divided by temperature in which the transition occurs, right? And so this transition occurs, this phase transfer occurs at transition temperature, right? Then the temperature of the surroundings is the same as this transition temperature, And so you'll have an overall delta S of the universe is going to be equal to 0 because delta S of the surrounding is just minus delta S of the system here, right? Which is telling you that, right, phase changes at the transition temperatures is a reversible process, right? It's a process at equilibrium, okay? And again, this reversible process is an equilibrium process, right? Systems at equilibrium have a net entropy of the universe equal to 0, right? Any transition that's occurring while at equilibrium has a net entropy change in the universe equal to 0, okay? So it is reversible. Reversible equilibrium, all these things are tied in together, okay? And so that does it for kind of this video. In the next set of videos, we'll start talking more about specific entropy changes and how we calculate entropy changes for different processes.